Thank you. Thank you. Thank you very much. I'm really honored to be here. And thank you for showing up at such a beautiful evening. Where I live, no one would have showed up with the weather like this. Of course, that's Phoenix, so weather's never like this. But I didn't understand the beginning, but I thank you. I assume you were apologizing for not giving me the Nobel Prize in 2012 when dark energy was discovered, but I accept that. In any case, I hope we'll have some fun tonight and motivate and justify your coming out here tonight. I put this up so that you'd have something to read when I was being introduced. But it also is relevant, actually, to the fact that I run this Origins project, because for me, the most important thing about mysteries is how you get there. And so what I want to do today, in some sense, is present to you a variety of mysteries, and I want to bring you up to speed about how we got there, and then talk about their implications. And indeed address what is probably a question that's been around for a long time, as was pointed out probably by Chris there. Why is there something rather than nothing? This question's been around for as long as people have asked questions. How did we get a universe full of stars and galaxies and everything that we see from nothing? And it was always been sort of the last bastion of God. And I'll talk about the fact that it doesn't have to be anymore. Now, there's a lot of ways to answer this question, but what I want to argue is that the way to answer it is to not decide the answer in advance, is to actually ask the universe. And that's a very important issue that I believe in strongly, that we should force our beliefs to conform to the evidence of reality rather than the other way around. I was just on a TV program in the United States earlier today trying to convince the Republican Party in my country to think that way. It hasn't worked yet. In any case, there are a lot of ways to answer the question. As I say, one of the ways is to just start, in the beginning, and then have a whole book that doesn't explain anything about anything. Or, as I say, to ask the universe. And that's what I want to talk to you about today. When we look out at this remarkable universe, there are 400 billion galaxies in our universe. This is a Hubble Space Telescope picture, one of my favorites, but they're all my favorite. Every dot on this image is a galaxy, not a star. Each galaxy contains maybe 100 billion stars, and some of these galaxies are over 10 billion light years away. And that means, as I'll describe later, that means that the stars that you're seeing, of course, emitted that light 10 billion years ago. So most of the stars in this picture don't even exist anymore. We're doing cosmic archaeology. That kind of, every time I look at a picture like this, it causes me to think and wonder about the universe in ways that are much more fascinating than myth and superstition, because the universe continues to surprise us in ways that our own humble imaginations would never generate. Which is why, by the way, in spite of my book, The Physics of Star Trek, why science fact is in fact much more interesting than science fiction. Okay, well, I want to begin sort of with the beginning. I want to begin with this fella here, who, as I often say, gives me great hope for humankind. This is Edwin Hubble, and he began life as a lawyer and then became an astronomer, so there's hope for everybody. Hubble was an amazing man in many ways, and in fact, while I want to talk about the discovery that's relevant, I want to briefly mention another discovery he made, in fact, with the Mount Wilson telescope. A single human lifetime ago, 87 years ago, the universe consisted of a single galaxy, our galaxy, at least the universe that scientists thought of. In fact, that it had been static and eternal. It had been around forever and would be around forever, and it had a single galaxy surrounded by a vast, eternal, empty space, a void. And that was the conventional wisdom just 87 years ago. And as I say, we now know there are 400 billion galaxies. And a single human lifetime ago, we knew of one of them. So it's not surprising. We're like the early map makers of the Earth. We're just beginning to understand the universe on largest scales. And so it's not too surprising that we're surprised all the time. Now, in fact, Hubble, the first discovery he made, in fact, was that there were other galaxies, that our galaxy wasn't the only galaxy in the universe. With the Mount Wilson telescope, he was able to discern that there were these objects in our galaxy called nebulae, which is Greek for fuzzy thing. And they were fuzzy things until you looked at them with the telescope, and then he was able to discern that they were in fact other galaxies around our own. And as I say, we now know there are 400 billion. But the key discovery that he made that changed everything was the discovery that the universe isn't static and eternal, that it's actually expanding. And that means it had a beginning, which is profoundly important for science and philosophy and even theology. Now, how did he do that? Well, I want to show you. This is the image that he's drawing of what he would have seen. These are galaxies. These are not sperm, though they look like sperm, but they're not. They're galaxies, and this is our galaxy. And what Hubble discovered is when you look out at distant galaxies, on average, they're all moving away from us. And those that are moving away from us, those that are twice as far away from us, are moving away twice as fast. And those that are 3 times as far away are moving 3 times as fast, and so on. So what does this tell you? What does this picture tell you? Well, obviously it tells you we are the center of the universe. But of course, as my friends remind me on a daily basis, that's not the case. It really tells us that the universe is expanding. But it doesn't look like that. It looks like we're the center. So how do we know it tells us the universe is expanding? I've tried a lot of different ways to explain this, but it's very hard to do because we live in our universe. Most of us live in our universe. As I say, the politicians in my country, many of them don't. But the only way to understand this is to get outside of our universe, which is hard in the real universe, but I can create a universe, a 2-dimensional universe, which we can get outside of. So here it is. I've drawn a universe, and I put galaxies at regular intervals, so you can see it at some time t1, and a later time, you can see it's gotten a little bit bigger, that slice of that universe. The galaxies are further apart. It's bigger. So if you were standing outside of that universe, you could see that it was expanding. But what would you see if you lived in that universe? Well, to see, we just have to pick a galaxy, any galaxy, say that one there. And to understand what it would look like from that galaxy, I want to superimpose this picture on top of this one, placing that galaxy on top of itself. So I'll do that. And what you see is exactly what Hubble saw. Every galaxy is moving away from you, and those that are twice as far away have moved twice the distance at the same time. Those that are 3 times as far away, 3 times the distance, and so on. And it doesn't matter which galaxy you pick. It's the same from every single galaxy. So it depends upon your mood. Either every place is the center of the universe, or no place is. It doesn't really matter. What it tells us is that the universe is expanding. And that's profoundly important, because it means it had a beginning. And we now know that beginning is 13.72 billion years ago, except in some places in my country like Alabama and Arkansas and Ohio and a few other places. But in the real world, it's 13.72 billion years old, so it had a beginning, which is important. But then the big question of cosmology became, how will the universe end? Because if it's expanding, will that expansion stop and slow down and recollapse? Or will it continue forever? And that became the question of cosmology. And in fact, the reason I got into cosmology as an elementary particle physicist is I wanted to be the first person to know how the universe would end. It seemed like a good idea at the time. And to determine how the universe would end, we have to know how much stuff there is in the universe. Because Einstein told us a remarkable thing in 1916, that space is curved in the presence of matter and energy. That space itself is a dynamical quantity. And the theory of general relativity describes the evolution of space, not how objects move through space, but space itself. And once we know space is curved, it turns out that space can have an interesting geometry. And it can exist in one of 3 kinds of geometry, so-called open, closed, or flat. Now, I can't draw for you curved 3-dimensional universes, because we live in 3 dimensions, so we can't picture in our brains a curved 3-dimensional universe. So I've drawn here curved 2-dimensional universes, but just to guide the eye. But just as in 3 dimensions, in 2 dimensions there are 3 different geometries. A so-called closed universe, the surface of a sphere, is a closed 2-dimensional universe. An open universe and a flat piece of paper. Now, I can't, as I say, draw these pictures in 3 dimensions, but I can tell you what would happen. In a closed 3-dimensional universe, if you looked far enough in that direction, you'd see the back of your head, because light would go around the universe. Space would close in on itself. This sounds very nice, but what's important is that in a universe dominated by matter, a closed universe will expand, slow down, and then contract in a big crunch, the reverse of the Big Bang. An open universe will go on expanding forever, and a flat universe is the boundary between the two. And of course, therefore, to determine the future, we had to determine which universe we live in. And since the geometry of the universe is determined by the total amount of matter in the universe, it just meant we had to weigh the universe. And that's all there is to it. Now, in fact, that's been an 80-year-long story about weighing the universe. In fact, I wrote a whole book about it at one point. But now I can tell you the answer because we've done it. And that's one of the remarkable developments that I want to talk about. These amazing developments in the last 40 years that have changed our picture of the universe in ways that we could never have imagined. Okay, but to do that, I want to do a little bit of history because there may be young people here who are thinking of going into a career in science. And when that happens, you will write scientific papers and you'll submit them to scientific journals like the journal Science, which is a distinguished scientific journal. And you will be rejected. But don't be disheartened. It's gotten harder. It used to be a lot easier. So I just want to show you that it used to be a kinder, gentler time. So I want to take you back to 1936 and the issues of Science magazine and a paper that was called Lens-like Action of a Star by the Deviation of Light in a Gravitational Field. Anyway, here's how the paper began. Some time ago, R.W. Mandel paid me a visit and asked me to publish the results of a little calculation which I had made at his request. This note complies with his wish. Try that today and see what happens. It was an easier time. Now, the author had credentials. His name was Albert Einstein, so I guess that helped. But what he calculated was something that he thought was entirely unimportant. He realized he'd already shown that light curves in a curved space, and therefore light bends around massive objects. That's what made him famous. But he realized that if you had a massive enough object and a source of light behind that massive object, the light rays could bend around and converge. And that object could act like a lens. It could magnify objects behind it, like my glasses do. Or if I had a cut glass goblet here and I looked at all of you, I'd see many different images of you in the room. And he realized that space can do that. But he said it would be unimportant, it would never be observable. And it was so unimportant, here's his calculation in 1936. And it was so unimportant that he forgot that in 1912, if you look at his journals, he did exactly the same calculation. He'd forgotten that he'd done it. And my favorite thing is if you look at his letter to the editor afterwards, he said, "Let me thank you for your cooperation with the little publication which Mr. Mandel squeezed out of me. It is of little value, but it makes the poor guy happy." That's how science is done. Well, he thought it was unimportant, but in fact it is important. It's the way we weigh the universe. Because here's a picture of the very phenomena that Einstein said we'd never, ever see. This is another Hubble Space Telescope image of a cluster of galaxies. Again, every point in this image is a galaxy, not a star. This cluster is 5 billion light years away from us, 5 billion light years. So the light left those stars before our Earth formed, since our Earth is only 4.5 billion years old. But clusters of galaxies are the biggest bound objects in the universe, so if we can weigh anything that can fall into anything will fall into a cluster. So if we can weigh clusters, we can weigh the universe. And we've been able to do that because of gravitational lensing. Because you don't have to be a rocket scientist to see there are these weird blue things in this image. And those blue things are multiple images of a single galaxy located 5 billion light years behind the cluster. 10 billion light years away from us, a galaxy that wouldn't even be observable, except it's magnified by space. And all these images are images of the same object. This is gravitational lensing. It's amazing, proof, of course, that space is curved. But we know the general theory of relativity. We know that mass curves space, so we can use this to weigh this cluster. Because we can ask how much mass would you have to put in that system, and where would it have to be in order to produce that image? It's a complicated mathematical inversion, as we call it, but you can do it. And when you do it, you get a picture that looks like this. Here's an image of where the mass is in that system. So the spikes are where the galaxies are. But you notice that there's a mountain of mass where the galaxies aren't. In between the galaxies, there's a huge mountain of mass. There's 40 times as much mass in that image as meets the eye. And in fact, around each galaxy, there are also mountains of mass that are invisible. 10 times as much mass in each galaxy as the visible stuff in the center. 40 times as much in this whole system. And this is true for every cluster that we see and every galaxy we see. The dominant stuff doesn't shine. And physicists are very creative linguistically, so we call it dark matter. And what we've discovered is that the dominant mass in the universe doesn't shine. There's at least 10 times as much stuff out there as meets the eye, as can be accounted for by all the stars and all the galaxies and all the hot gas and everything. Now, what makes that incredibly exciting for me and others is that we know for other reasons that, in fact, there aren't enough protons and neutrons, the stuff that makes all of us up, to account for this material by a factor of 10. So we're virtually certain that this dark matter is made of some new type of elementary particle, not present in any of your bodies. That makes it exciting because that means we can look for that material without telescopes. Because that means if it's a gas of elementary particles, it's not just out there, it's in this room. It's going right through your bodies as you nod off as I talk. And that means we can build detectors here on Earth and underground, in fact, to look for it. Because I think I have a picture of a detector. Yeah, one that I proposed many years ago that's now being built. I just came back from outside Rome looking at these kind of detectors. I tweeted that I went to Rome on Tuesday for a closed-door meeting, and I did, but it was a different one. Anyway, mine had content. But anyway, I couldn't resist. This is a dark matter detector. It's kind of neat because we put them deep underground. Because why deep underground? Because we are bombarded every day by cosmic rays that go right through us and sometimes cause cancers and things. But if we put a detector deep underground, the rock will shield it. And these dark matter particles, which we think interact very weakly with normal matter, on average go right through the Earth without even knowing it was there. So they go right through the Earth and right through this detector. And here's a block of germanium. We cool it down to 1/1000th of a degree above absolute zero. And most of the time, the dark matter particles will go right through it. But every now and then, we think a dark matter particle may bounce off the nucleus of an atom of germanium and heat the whole thing up by 1,000th of a degree. And maybe once a year that'll happen, so we put these things in with no radioactivity. It's a very complicated thing. And there are detectors like this being built all around the world, in deep mines, in Europe, Japan, Canada, the United States. And we hope in this way to discover the identity of this dark matter. But it's even more exciting too because you see, it's a race. Because these dark matter particles were created at the beginning of time, we think, in the Big Bang. So one way to look for them is to look for the remnant particles that are here today. But another way is to create a mini Big Bang and maybe produce them in the laboratory. And we're doing that at the Large Hadron Collider. Not right now because the machine's turned off. But we recreate the conditions in a very small region. We recreate the conditions of the early universe when it was 1/millionth of a second old at the Large Hadron Collider. And therefore, in fact, we're hoping to produce the dark matter particles there. So there's a race between these people here who are trying to directly detect it and the people of the Large Hadron Collider. We don't know who will win, or maybe neither of them will. And it will be very important because we will learn the identity of the stuff that makes up most of the universe. But for our purposes here, it doesn't matter what it is. What matters is how much of it there is. And that, therefore, we just have to weigh it. And so we go back to this image, and this image tells us how much mass is in this system and other systems like it. And we have finally, after 80 years, we have weighed the universe. And here's the answer. I should have a drum roll. There it is. I see people fainting in the back. Well, when physicists have an important number, they give it a Greek letter, because we like to sound scholarly. So we call it omega. And omega is the ratio of the actual amount of matter in the universe divided by the amount you'd need to make a flat universe. And by the way, just so I know this question will come up, a flat three-dimensional universe is not flat like a piece of paper. It's flat in the sense that it's the universe you always thought you lived in, where the three axes, the x, y, and z axes, are perpendicular and light travels in straight lines. It's the universe you thought you lived in, no curvature. And so if the universe were flat, omega would be 1, because this is the ratio of the actual amount of matter divided by the amount of matter to make a flat universe. If it's less than 1, the universe is open. If it's greater than 1, the universe is closed. And you can see that we have finally, with great effort, definitively shown that there's only 30% of the amount of stuff in galaxies and around galaxies to make the universe flat. So we appear to have answered the holy grail of cosmology. The universe appears to be open. But there's a problem. The problem is that we theorists, I'm a theoretical physicist, and we theorists knew the answer. We always know the answer. We're not often right, but we always know the answer. And we knew that we live in a flat universe because it's the only mathematically beautiful universe. Okay? And these observers were getting it wrong, as they usually do. It was very frustrating. But in fact, we realized that, okay, well, in fact, while all the evidence was for an open universe, there's a problem here. The problem is that if you're weighing stuff around galaxies, you could miss stuff. Moreover, it's a very indirect way to determine the curvature of the universe, to weigh all the stuff in it, then plug that into Einstein's equations and calculate the expansion of the universe and work out its curvature. Wouldn't it be better to measure the geometry of the universe directly? Of course. And the other amazing thing is, in the last decade or so, we've been able to do that. And I want to show you how. So how would we measure the geometry of the universe? Well, let's start more simply. How would you measure the curvature of the Earth if you couldn't go around it and you couldn't go into outer space? How would you measure that it's curved? It's quite simple. You just draw a triangle, and then you ask a Swedish high school student, not an American one, what are the sum of the angles in a triangle? And they'll tell you it's 180 degrees. And that's right. That's because they learned their geometry from Euclid. But on a curved surface, it's very different. Take the Earth, for example. I can draw a triangle on the surface of the Earth that's quite different. So I draw a triangle. I draw a line along the equator. I go up to the North Pole. Then I come back down. And I've got a triangle with 3 right angles. 3 times 90 is 270. So that would tell us if we drew a big enough triangle on the surface of the Earth, we'd know it was curved, because some of the angles wouldn't be 180 degrees. Well, it turns out that's precisely true, not just for a curved 2-dimensional surface, but for a curved 3-dimensional space. If we could find a triangle that was big enough and measure the angles in that triangle, we could directly measure the curvature of the universe, and that's what we've been able to do. Using the most important observation in cosmology for a long time, the cosmic microwave background radiation, the afterglow of the Big Bang. So what's that stuff? Well, we're sitting here and we look out at the universe and we see galaxies that are, say, 1 billion light years away. That means the light was emitted from them 1 billion years ago. So when we look out at the universe, we're doing cosmic archaeology. We're looking back in time. Now, if the universe is 13.7 billion years old, then you'd think if you looked out far enough, you'd see the Big Bang. And you could, in principle, except between us and the Big Bang, there's a wall. Not a physical wall, but essentially a metaphorical wall, just like this one, in a way. Because if we look out at the early universe, at earlier and earlier times, the universe was hotter and hotter. And if we go back to a time when the universe was 100,000 years old, just 100,000 years after the Big Bang, the temperature in the universe was 3,000 degrees above absolute zero. And at that temperature, hydrogen, which is the dominant stuff in the universe in normal matter, gets broken apart. Protons and electrons get broken apart. Every time hydrogen tries to bind together and be neutral, the radiation would break it apart. So that meant before this time, matter wasn't neutral. You'd have protons and electrons, and you'd have what's called a charged plasma. But a plasma is opaque to radiation. You can't see through a plasma. So it's just like this wall, this curtain here. It's opaque. And if we think about what happened, then at all earlier times the universe was opaque, and then suddenly, at 100,000 years, It cooled enough so that protons captured electrons. You got neutral matter. Neutral matter is transparent to radiation, so that radiation can come all the way from there to us. And one of the predictions of a Big Bang is that there should be radiation coming at us from all directions. And of course, the universe has cooled since that time. It was 3,000 degrees then, it should be 3 degrees now. And that was the radiation that was discovered by accident in New Jersey, of all places, in 1965 by two people who didn't know what the hell they were doing. But they won the Nobel Prize anyway. Because as you'll verify, you don't actually have to know what you're doing to win the Nobel Prize. I don't mean that in a negative sense. You just have to discover something important. You don't have to anticipate it. And this was very important. It was the afterglow of the Big Bang. Actually, if you're old enough, many of you have seen it yourselves. If there's a question period, I'll answer where that comes from. But now, and in fact, 2 Nobel Prizes have been given for this, because if you could actually image that surface, you'd get a picture of the baby universe, and I'll show you that picture in a moment. But on this surface, what's called the surface of last scattering, the moment when the universe became neutral, there's one important length scale, and it's 1 degree. Why? Well, that represents a length on that surface of 100,000 light years across. The universe is 100,000 years old. Einstein told us that no information can travel faster than light. Therefore, anything that happens here on that surface cannot have affected anything over here, because light couldn't have traveled across that far. It can only, this is how far light can have traveled in 100,000 years. This is very important, because it means if I have a lump of matter that's that big, well, gravity works, it starts to collapse, it heats up, all sorts of interesting things happen. But if I have a lump that's this big, it doesn't even know it's a lump. It doesn't know it's supposed to collapse, because gravity travels at the speed of light as well. So the largest lumps that will have collapsed at this time are 1 degree across. But that gives us a ruler. Because if you think about it, we're looking back at that surface at a 100,000 light year across ruler. And in a flat universe, light rays travel in straight lines, so that ruler will span 1 degree on my eye. But in an open universe, light rays diverge as I go back in time, so the same ruler will look smaller, maybe just a half a degree. And in a closed universe, light rays converge as I go back in time, so the same ruler will look bigger. So all we have to do is take an image of that surface and ask how big are the lumps. Half a degree, 1 degree, or 2 degrees, and we'll see what will measure directly the geometry of the universe. And that's what we've been able to do. This was one of the first experiments that did it. This is called the boomerang experiment. It's a balloon with a microwave radiometer, because this radiation comes in the microwave band. And it went way above the Earth's surface, and it went around the world, which is easy to do in Antarctica. You just do this if you're at the South Pole. But it didn't. It was at the edge. It took about 2 weeks to go around. It came back, and it produced an image of the microwave background radiation. This is a false color image, because this is microwave radiation. But here are the lumps, the hot spots and the cold spots in the microwave background that we think were created at the very beginning of time, that later on would collapse to form galaxies and stars and planets and aliens and everything else. But the question is, let's try going back and back. There we go. Okay, I'll try this again. Here we go. The question is, how big are these lumps? Are they 1 degree, half degree, or 2 degrees? So to do that, we, as you've now seen in this next slide, we create universes on a computer. We build universes on a computer, a closed universe, a flat universe, an open universe, and we randomly put down lumps and we ask, how big would they look? This is the same image but different colors. And in a closed universe, 100,000 light year across lump would on average be about that big, but that's bigger than these lumps. In an open universe, 100,000 light year across lump would be about that big, but that's smaller than these lumps. But just like Goldilocks, in a flat universe, it's just right. And we now know to an accuracy of 1% that the universe is flat. So if you're a theorist like me, you do this. You pat yourself on the back. because we knew the universe was flat. But you'll notice there's a problem. 10 minutes ago, I showed you the universe was open. There's only 30% of the amount of stuff needed to make a flat universe. 70% of the energy of a flat universe is missing. Well, if it's not where galaxies are, it must be where galaxies aren't. But what is where galaxies aren't? Nothing. Now, if nothing weighs something, we're okay then. But that's crazy. Nothing can't weigh something. Well, the universe is crazy. Or can be. That's one of the other things. I was just debating these Islamic people. I was trying to explain to them that actually, and I've done it with some philosophers too, so we may do that, that classical notions of what's sensible are irrelevant. The universe doesn't exist to make us happy. And therefore, we have to realize the universe can be stranger than our imagination. Now, it turns out, when you take quantum mechanics and relativity and put them together, as Richard Feynman showed, in fact, it implies that empty space ain't so empty anymore. It's a boiling, bubbling brew of virtual particles popping in and out of existence in a timescale so short that you can't measure them. They're called virtual particles. There are no real particles there. If you look, you won't see anything. But there are particles popping in and out of existence, but they're disappearing so quickly you can't see them. Now that does sound like philosophy or theology, because, you know, it's like sounds like counting angels on the head of a pin or something. But it's not. If it was just a story, then it would be. But while you can't see these particles directly, you can see their effects indirectly. And here is a picture, actually an animation, of what the space inside of a proton looks like. It's actually was first shown here in Stockholm when I was here in the Nobel Prize ceremonies in 2004 by the people who developed the theory that allowed the calculation to be done. This is the space inside of a proton. Now, if you went to a good high school, you might know that a proton's made of things called quarks, supposedly 3 quarks. Ever heard that? Okay. Well, we lied. It is made of 3 quarks, but it turns out if you add the mass of those quarks up, they only add up to 10% of the mass of the proton. 90% of the mass of the proton comes from these virtual particles and fields that are popping in and out of existence in a time scale so short you can't see them. And we can calculate that effect. That's why they won the Nobel Prize. So we know, even though we can't see them directly, that these particles, virtual particles, pop in and out of existence. Well, if they can contribute to the energy of a proton, we can do a calculation and ask how much energy would virtual particles contribute to empty space. And we do the calculation, and we come up with the worst prediction in all of physics. We calculate that the energy of empty space should roughly be a gazillion times the energy of everything we see. Now, that's impossible because we wouldn't be here if that was the case. It turns out we calculate that the energy should be 120 orders of magnitude larger than everything we see, which can't be the case. And as I say, therefore, we know it can't be bigger than the energy of everything we see, more or less, or not much bigger. And so we know, and this problem has been around since I was a graduate student, we calculate a number that's 120 orders of magnitude too large. It is the worst prediction in all of physics. But we know the answer, because we're theorists. Or we knew the answer. We knew the answer had to be 0. Because 0 is a nice number. I mean, if you wanted to make it not 0, you'd have to cancel this big number to 120 decimal places and leave something non-zero in the 121st decimal place. No one knows how to do that. But 0 is a number that's easy to get. Because mathematical symmetries can make numbers equal and opposite, and they can make things cancel exactly. So from the time I was a student, we knew the answer was 0. There must be some new symmetry of nature which would cancel things out exactly. It would be 0, it would be sensible, and we could sleep at night. But cosmology is a science. And that means just because it's sensible isn't good enough. We have to go out and measure it. Well, how could we measure energy in empty space? Well, it turns out if you put energy in empty space, Einstein tells us that energy is gravitationally repulsive, not attractive. It blows, it doesn't suck. And that means if I put energy in empty space, the expansion of the universe won't slow down, it'll actually speed up. if I try and measure the expansion rate of the universe over time, if I put energy in empty space, the expansion will get faster and faster and faster. Well, in 1998, two groups of astronomers who really didn't know what the heck they were doing went out. Oh, actually, before I do this, I want to go back and there's a long history of making mistakes in astronomy, so I want to go back to it. This is actually Hubble's data. This is Hubble's data from 1929. This is the velocity of distant galaxies as a function of their distance. And this is one of the reasons he knew he was such a great scientist. He knew to draw a straight line through that data set. Not obvious at all. And Hubble measured this expansion rate, and he got the answer wrong by a factor of 10, which is very important. Astronomers have tried to emulate that ever since, as I say. And it was very profoundly important that he got it wrong by a factor of 10 because it was a real puzzle. Because he discovered that the universe was expanding 10 times faster than it actually is. But if it's expanding 10 times faster than it actually is, you can calculate the age of that universe, and it's only 1.5 billion years old. This was very embarrassing in 1929, because already then we knew the Earth was older than 1.5 billion years old, and it really is embarrassing when the Earth is older than the universe. But happily, he got it wrong. He got it wrong not because he wasn't a good astronomer, but because it's hard to measure. You can measure the speed of objects away from us, but how do you know their distance? Distance is hard to measure. We don't have rulers that are that long. How can we measure the distance to distant objects? Well, we use physics. I can measure the distance to that light bulb that's showing this picture, for example, if I took out the lens. If you're old, a lot of you look like you're old enough to remember light meters on cameras. Okay? If you had a light meter, if I knew there was a 100-watt light bulb in that projector, and I took out the lens so it was spread out uniformly in all directions, and I saw 1 watt of light coming into my light meter, I could work backwards and figure out how far away I was from the projector, okay? Because I know how light spreads out. So if the universe were full of 100-watt light bulbs, we'd be fine. But it's not. So we have to find the equivalent, something we call a standard candle, something whose brightness we think we understand for other reasons, and then we look at it through a telescope, and we see how bright it looks, and from that we can tell how far away it is. And we have found, finally, after 80 years, a standard candle. These two groups of astronomers found this standard candle and worked with it. Here it is, right here. This is a galaxy far, far away, long, long ago. Actually, not that far. It's only about 70 million light years away. And here's a star. And you can see this star is burning with a brightness equal to the brightness of the center of that galaxy, containing 10 billion stars. How can that be, that star could be as bright as 10 billion stars? Well, the first assumption could be it could be a star in our galaxy that got in the way of the picture, which is a good thought, but it's not. It's actually a star at the edge of this galaxy burning with a brightness of 10 billion stars. Why? It's a star that's just exploded. It's a supernova. The brightest fireworks in the universe. When stars explode, they briefly shine over a period of a month with a brightness of 10 billion stars. And this is one. Now, fortunately for us, stars don't explode too often. But fortunately for us, they explode. You wouldn't be here if they didn't. Because every atom in your body was once inside a star that exploded. And as I often say, the atoms in your left hand were in different stars than your right hand, probably. You are literally stardust. Every atom in your body has experienced the most violent explosion in nature, maybe not just once, but many times. You are children of the stars. Why? Because the only elements made in the Big Bang were hydrogen, helium, and lithium. But all the important stuff, well, lithium may be important for some of you, but all the rest, for the rest of us, carbon, nitrogen, oxygen, iron, all those things are only made inside the cores of stars. And the only way they could get into your bodies is if the stars were kind enough to explode. So it's amazing that you are, to me, it's the most poetic thing I know about the universe. And in fact, I wrote a whole other book about it because I think again, that just amazes me. But as an aside, that's interesting. But these stars, I tell you, don't explode very often. It turns out they explode once per 100 years per galaxy, on average. So how can we measure them? Well, the simple thing is you assign a graduate student to each galaxy. 100 years is about the right time for a PhD. The graduate student dies, they're cheap, you just get another one. But we don't need to do that, because the other thing that's really important to remember about the universe in which we live is it's big and it's old. And that means rare events happen all the time. And amazingly, if you go out in the night sky tonight, if it wasn't snowing, it was a clear night, and you got out of Stockholm, and you took your hand and you put maybe, I think it was I forget what coin it was that was so, I think it was a half a kroner. Anyway, it's a small coin that I got, one of your coins. If you held up a hole in your hand about that size and held it up to a dark spot in the sky where you couldn't see any stars, if you looked at that region with one of the biggest telescopes we now have on Earth in Chile, you'd see 100,000 galaxies. And if you work it out, once per 100 years per galaxy, in that region, you're going to see on average a given night a few stars explode. And astronomers do that. They apply for telescope time, and they say, tonight I'm going to see a few stars explode, and they might see one star, they might see two, they might see none, it might be cloudy. But that way we can actually study supernovae, and here they are. Here's a movie of a star exploding in this galaxy. And this type of exploding star is called a type 1a supernova. We can tell by looking at the colors. And for reasons I won't go into, it turns out that that is a wonderful standard candle. Those type of supernovae, we believe we understand their brightness intrinsically, and then we can look and see how bright they look, and they're so bright we can see them across the universe. So we can see them in galaxies billions of light years away, and therefore we can measure the speed of those galaxies and their distance, and measure the rate at which the universe is expanding. And that's what these astronomers decided to do. And the first thing they did was redo the Hubble curve. You can see it's much better. This was after the important discovery that on a log-log plot, everything's a straight line. But anyway, with this new data, we can now tell the Hubble expansion rate not to a factor of 10 uncertainty, but to 10%. So we know how fast the universe is expanding. But what we care about is what happens at the edge. Is the Hubble plot turning down or not? Is the universe decelerating? And in 1998, two groups of people decided to try and measure how fast the universe was slowing down. And this is their data. It was the cover of Science, and turned out. This is distant supernovae, and they wanted to see how the curve was turning down. To see what was happening here, I just draw a straight line through the data set and bring the whole thing over and make it horizontal. And what they expected to see for distant objects was that these supernovae fell along this curve as the universe was slowing down. But much to their amazement, the supernovae didn't lie on that curve. They didn't even lie in the straight line. They lay above the straight line. How could that be? Well, there's two possibilities. One, the data's wrong, which it usually is. Or two, the universe isn't slowing down, it's actually speeding up. And if you just naively say, how much stuff is there would you have to put into empty space? How much energy in empty space would you need to fit the data, that curve there? You need exactly what we were missing. If you put 70% of the energy of a flat universe into empty space, everything works out. And you can win a Nobel Prize for that, which they did. So everything holds together with this cockamamie universe, and that is quite remarkable. And it leads me to the first thing I want to tell you before we get to the second half, or the last little bit of the talk. What this tells us, and what it should tell you, is that you are much more insignificant than you thought before you came into the lecture. Because 70% of the energy of the universe resides in empty space, but 30% of it resides in dark matter, and 1% of it is everything we see. All the stars and galaxies account for 1% of the universe. We're just a little bit of cosmic pollution in a universe full of dark matter and dark energy. So much for a universe made for us. But that is a remarkable discovery. It's so important that I want to just remind you. So much ado about nothing. Nothing is almost everything. And that's a key point. Our ideas of nothing have changed. So the dominant energy in the universe resides in empty space. We don't have the slightest idea why it's there. And if someone comes here and lectures to you and says they know, they're lying. Especially if they're a string theorist in the back of the room. We think its existence is tied to the very beginning of space, and more important, as I'll show you, It will determine our future. Now, these set of discoveries, so that's our current picture of the universe. And now I want to ask, what are the implications of that for our understanding of the origin of the universe? To do that, I want to just remind you of the reason I got into cosmology. How will the universe end? And we can actually determine what will happen to the future of the universe if it's full of matter using, in fact, high school physics. So I want to take you back to a time that all of you love, high school physics. And I want to ask, how can we determine if a coin that I throw up will come back down? So I take a coin, I throw it up, it comes back down. I throw it up faster, it goes up higher, it comes back down. If I throw it up really fast and there's no ceiling, it doesn't come down at all. It escapes from the Earth. Now, we teach students how to calculate that escape from the Earth by talking about energy. So we say that coin has two bits of its energy, a positive piece and a negative piece. The positive piece we call the kinetic energy, and it doesn't matter what the equation is. It's related to the speed of the coin. And the negative piece is related to the gravitational pull of the Earth. And it turns out this just becomes a bookkeeping problem. If the total energy is bigger than 0, if this term beats that term, the coin will escape. If the negative piece beats the positive piece, the coin will return. Well, it turns out that same calculation we can do for the whole universe. Here's that picture I showed you of Hubble. Here's our galaxy. If the universe is the same everywhere, then to determine what's going to happen to the whole universe, we just have to determine what's going to happen to a single galaxy. Because if it's going to return, they're all going to return. So look at a small region of the universe, and look at that galaxy, and we just have to calculate its total energy. So we calculate the positive piece, but the positive piece depends on its velocity, which Mr. Hubble told us. That's the expansion rate. The negative piece comes from the gravitational attraction of all the stuff inside this sphere. That's matter plus dark matter. We add all that stuff up, and we get the negative piece, and we compare the two. And if the negative piece beats the positive piece, if the gravitational attraction beats the velocity, the galaxy is going to come back. And if the positive piece beats the negative piece, the galaxy is going to escape. So if B over A is bigger than 1, the negative piece beats the positive piece, the universe would collapse. It's full of matter. If B over A is less than 1, it will expand forever. But what is remarkable is B over A is nothing other than this quantity omega, the curvature of the universe. And we've learned the answer. We live in a flat universe, so omega is 1. But if omega is 1, what does that mean? That means that B is precisely equal to A. What does that mean? That means the negative piece is precisely equal to the positive piece. What does that mean? That means the total gravitational energy of every object in a flat universe is 0. Now, if you were going to make a universe from nothing, what would you make the total energy of every object? So this gets you thinking. So I want to now spend the last few minutes talking about how all of this tells us, remarkably, that the universe can come from nothing without any supernatural shenanigans. And I want to be careful here and talk about different kinds of nothing. The philosophers especially like me to do this, or they don't like me to do this, depending upon the philosopher. But the first kind of nothing I want to talk about is just empty space. The kind of nothing in the Bible, in fact, a dark, eternal void. Well, it turns out that kind of nothing is unstable because that kind of nothing is full of virtual particles that are popping in and out of existence in a time scale so short you can't see them. Well, that's not matter. That's not galaxies and stars. But once you add gravity into the mix, things change. Because the reason virtual particles have to disappear quickly is because they violate energy conservation. You create them, and they have energy, and they have to disappear before you can measure that energy. But if you create virtual particles that have 0 total energy, they can exist forever. So once you allow for gravity in the mix, and gravity allows for negative energies, you can create particles with impunity. And in fact, you are guaranteed that if you wait long enough, empty space will start spewing out particles. So, in fact, empty space is unstable. And then the answer to the question, why is there something rather than nothing, is really not so... The real interesting question would be, why is there nothing rather than something? But of course, you wouldn't be around to ask the question if there were. So in fact, if you wait long enough, you're guaranteed to have something. Empty space, nothing, will create something, and it can create enough matter to make 400 billion galaxies, each containing 100 billion stars. It doesn't violate any laws of physics. But you might say, if you don't like this, and this is what I just, so if you don't like that, you might say, okay, but that's empty space, but where did the space come from? I mean, there's space after all, that's not nothing. Well, once I consider the quantum mechanics of gravity itself, then things change. Because you see, virtual particles tell us that there's fluctuations in empty space due to quantum mechanics. But if we were to make a quantum theory of gravity, which we don't have yet, string theory notwithstanding, that quantum theory of gravity, the variables of gravity are space and time. If they become quantum mechanical variables, then you won't just get particles fluctuating in space, you'll get spaces popping in and out of existence as well. Space and time can be created where there was no space and no time. And it's happening all the time right now on microscopic scales. Microscopic universes are popping in and out of existence all the time, but they go out of existence in a time scale that's very short. The only universes that could survive long enough for us to have this little discussion are universes that have zero total energy. Those universes could survive forever. So quantum mechanics would tell us if you pop a universe, and that means popping space and time out of nothing, if it has zero total energy, it can survive for a long time. Well, everything begins to sound good, because I told you the universe in which we live, a flat universe, every object has total gravitational energy zero. But it's not so simple. I wish it was. Because I didn't take into account other kinds of energy. And it turns out the only kind of universe that we know that has zero total energy is not a flat universe, but a closed universe. Okay. But most closed universes that you create will expand and then contract in a very short time. The only kind of closed universe that can live long enough for us to be there is one that doesn't do that. Well, how could you stop it from doing that? Well, if you put energy in empty space in that closed universe at early times, it could puff up that closed universe, making it very, very big. Well, it turns out, for totally independent reasons, our theories of particle physics tell us, and told us well before we had this argument, told us that in fact everything we know about particle physics tells us that in the early history of the universe, empty space probably stored a lot of energy, and it puffed up by a huge amount in a very short time. This idea called inflation. Given what we know about particle physics, we have every reason to expect that when the universe was a millionth of a billionth of a billionth of a billionth of a second old, there was a huge amount of energy stored in empty space that caused the volume of space to increase by 90 orders of magnitude in a millionth of a billionth of a billionth of a billionth of a second. It sounds like science fiction. But interestingly enough, that theory is not just a story. It makes predictions. And one of the predictions it makes is what the little fluctuations that later on would produce all the stars and galaxies would look like. And they look just like the image in the cosmic microwave background radiation. So we had great faith that these ideas might be right. We now have even more faith because of beer. I grew up in Canada. Beer is very important. Some of you may have had this experience, not the young people, I hope. Let's say you have a party and you get some beer for everyone, but you forget to put it in the refrigerator. And you go, oh my. So you put it in the freezer. But then if you're like me, you forget that you put it in the freezer. And after the party's over, you open up the freezer and you see the beer, and you open it up and crash. You open a bottle and it crashes open. Why? Because when it was under high pressure, the beer was liquid. I open it up, and suddenly the pressure goes away and the beer freezes, and energy is released enough to crack open the glass of the beer. That's exactly what we think happened in the early universe. That as the universe cooled, the universe got stuck in what we call a metastable state. There was some field everywhere throughout all of space that got stuck. And then, boom, it released, and when it was stuck, the expansion of the universe speeded up for a long time, and then, boom, that energy was released, producing a hot Big Bang. Again, that sounds fantastical, except one of the great things about the discovery of the Higgs particle, which will soon win a Nobel Prize, this year or next, is that it means the Higgs particle tells us that there can be fields throughout empty space that get stuck. The Higgs field is such a field. So this whole picture makes much more sense after the Large Hadron Collider than it had before. But it tells us that, in fact, inflation, if it happened, will force the universe to look very flat. The only kind of closed universe that won't collapse in a microsecond is one that puffs up because of inflation. But just like blowing up a balloon and getting very big, the Earth looks flat in Kansas. And the universe, if it blew up so big, will look flat. So the only closed universe that could survive long enough for us to be here would look flat. Just like the one we appear to live in. So, if you were going to create a universe from nothing, now let me remind you, this is the kind of nothing I'm talking about. No particles, no radiation, no space, no time. Nothing. If you were going to create a universe from nothing, what would it look like? It would look like the universe in which we live. Now, does that prove our universe came from nothing? No, but it makes it plausible. And that, to me, is worth celebrating. It's like my friend Richard Dawkins wrote the afterword for my book, and it was kind of hyperbolic. He compared it to the origin of the species, which was nice of him, but it's not. But in one way, it's the same, in the sense that before Darwin, everything was a miracle. Every form of life was created specially for its environment. But Darwin showed it was plausible, given what he saw in biology, it was plausible that the incredible diversity of life originated by natural causes from a single species. He didn't know about DNA, he didn't know about genetics, but it was plausible. That's exactly where we're at in cosmology now. We're at the point where we can show that it's plausible to create a universe from nothing, and you don't need God to do it. It doesn't violate any laws of physics. Now, you might say, if you're perverse, that that's not nothing. Because you got no particles, no radiation, no space, no time, but where did the laws come from? Well, even the laws themselves could have arisen in our universe, and I want to close with that. And the reason we now think that comes from this picture. It's the last time you have to think in this talk, okay? So let's work together on this. This is a brief history of time. This is a history showing the density of matter in the universe. As the universe expands, the density goes down. And this is the energy density of empty space, which remains constant. Now, we live right here, when the energy of empty space is 3 times the energy of matter. But if you stare at this long enough, and physicists have, you go crazy. Because there's something strange about this. We're living in the only time in the history of the universe when these two numbers are the same. At all earlier times, the energy of matter will exceed that in empty space, and at all later times, the energy in empty space will exceed that in matter. We're living at a very special time. But Copernicus told us we're not supposed to live in a very special time. There's nothing special about 13.7 billion years. So why should this be the case? Well, physicists have come up with this answer. Galaxies exist. Why is that? Well, because let's look at this, and let's just say the energy of empty space were 50 times bigger. Then these two curves would not cross today, but here. Well, then these two curves would cross there. What time is that? That's the time when galaxies first formed. But if the energy of empty space exceeded that in matter before galaxies formed, then galaxies wouldn't form. Because the energy of empty space is gravitationally repulsive. So if galaxies didn't form, then we wouldn't be here. And this has led physicists to this crazy idea, which I call anthropic mania. If there are many different universes, and the energy of empty space can vary in each universe, it's a random variable, then only those in which it's not much greater than what we measure today will galaxies form, and only then will stars as planets form, and only then will astronomers form. So the universe is the way it is because there are astronomers here to measure it. It sounds ridiculous. It sounds almost religious. It's not. It's kind of a cosmic natural selection. You wouldn't expect to find yourself in a universe, living in a universe in which you couldn't live. You'd be quite surprised. That would be worth writing about. Okay, great. Well, I've got about 5 minutes. Okay, good. Just so you're getting the hook here. Okay. This is depressing if it's true, because it means this fundamental quantity in our universe, the energy of empty space, is an accident. There's no fundamental theory of why it has the value it has. There are many universes, maybe, and it's just an accident. Now, you see, particle physicists are way ahead of cosmologists, because in cosmology, there's one number we don't understand. In particle physics, there's many more numbers we haven't understood for much longer. We don't understand why gravity is the weakest force in nature, why the proton's 2,000 times heavier than the electron, why there are 3 generations of elementary particles, etc. We don't understand any of that. We've been trying to understand it since I've been a student. But particle physicists have leapt on this and said, maybe we don't have to understand anything. Maybe it's all an accident. Maybe every one of those quantities is an accident. If they were different, we wouldn't be here. Then we don't need a theory of everything. We just need a theory of anything. Well, we have such a theory. It's called string theory. So I do want to show you one slide on string theory. This is a history of string theory over the last 40 years. One guy says to another, I just had an awesome idea. Suppose that all matter and energy is made of tiny vibrating strings. The second guy says, okay, what would that imply? The first guy says, I don't know. So that's the story of string theory. It used to be a theory of everything, but instead, in fact, it's a theory. Well, string theory requires extra dimensions, but we don't notice them when we walk around, so we get rid of them by compactifying them. But and maybe 6 or 7 extra dimensions, maybe in very small scales, we can't see them. It sounds very nice, but each different way you compactify those extra dimensions produces a different 4-dimensional universe with different laws of physics. That was a bad thing. But string theorists, every wart becomes a beauty mark in string theory. Now they call it a landscape. Because it turns out there could be 10 to the 500 different universes depending upon how you compactify the extra dimensions. And one of them, at least, is guaranteed to look like ours. Because the laws of physics are different in every one. Is this science? I mean, if you could explain any universe, then you can't falsify the theory. But it may be true. It may be true. And if it is true, it means the very laws of physics that we measure are accidents. They did not exist before our universe existed. So in that case, you start out with no laws, no space, no time, no particles, no radiation. To me, that's nothing. Okay, to conclude in honor of my late friend, Christopher Hitchens, he pointed out another argument about nothing. Nothing is heading straight towards us. Because, in fact, as I explained to him, the future is miserable. And I think, well, let's see. Yeah, okay, the first person to realize the future is miserable is George Orwell, as you know. He said, to see what is in front of one's nose requires a constant struggle. And this is, of course, what he meant by it. What that means is, in a universe with energy and empty space, it's going to speed up faster and faster and faster. And eventually, objects greater than a certain distance away from us are in fact receding from us faster than the speed of light. It's happening now. It's allowed. You know, you think we tell you nothing can travel faster than the speed of light, but we lied. It's true that nothing can travel through space faster than the speed of light, but space can do whatever the hell it wants. And space can carry objects away faster than light, and it's happening today. And if the universe is speeding up, it's happening faster and faster and faster. And galaxies we now see will in the far future be moving away from us faster than the speed of light. I think I'll skip that. And that means if we wait long enough, the rest of the universe will disappear before our very eyes. In 2 trillion years, all of the galaxies we now see will have disappeared. And the universe will become cold and dark and empty. And that means In fact, it's rather poetic. In the far future, there'll be observers, there'll still be stars around, there'll be carbon-based life forms, and they'll evolve, and they'll discover quantum mechanics and electromagnetism and general relativity. They'll build telescopes. And when they look out, what will they see? They'll see the universe we thought we lived in 100 years ago. They'll think they live in a universe with a single galaxy surrounded by an eternal, dark, empty space. They won't know that the universe is expanding. They won't know there was a Big Bang. The future will indeed be miserable. And by the way, that's the second of the two things I wanted to remind you of. First, you're insignificant, and second, the future is miserable. So what this did and for Christopher is gave a new answer to the question, the last one I want to give. Why is there something rather than nothing? The answer is quite simple. There won't be for long. Because we have this cosmic hubris that makes us think the universe is always going to be the same. If we wait long enough, everything we see will disappear. So to conclude, happily, science has demonstrated that a universe of nothing is not only plausible, but likely. And what we mean by something and nothing has completely changed. This issue will become important, I'm sure, in the panel. It's changed from the time the classical philosophers and theologians first raised the issue. What we mean by nothing is totally different. And what we mean by something is totally different than Aristotle discussed, or Descartes, or any of them, because they didn't know about quantum mechanics. The very question, why is there something rather than nothing, is not the interesting question. Why questions are not interesting. Why questions aren't even questions. Because why questions presume purpose. Everyone knows, if any of you have children, know the only way to ultimately answer the infinite series of why questions is to say, because, go to bed. The really interesting question is how. How did the universe evolve, and how can we find out? And that's what we're working on. And it's an incredibly exciting activity. And so, as we look out at the night sky and remember the fact that you are insignificant and the future is miserable, you shouldn't be depressed. You should be excited, because here we are at this random moment in time, 13.7 billion years after the Big Bang, in this random place in the middle of nowhere, but we're endowed with a consciousness